Hello everyone, I'm Zhiyi and I will talk about typo inference today. I'm currently working on a Haskell project. It's a live functional programming environment featuring typed hosts, and it's a gradual typing system. So we want to add type inference for the Haskell. We look into two existing methods for type inference, bidirectional typing and constraint-based type inference. Bidirectional typing, or on the other words, local type inference, used in language like Scala and TypeRacket, have a simple algorithm for static type checking and can generate clear static error messages, but it requires programmers to do lots of type annotations. On the other hand, constraint-based type inference allows programmers to omit most of type annotations, but it has a complex algorithm and it's hard to do error reporting. So we want to borrow ideas from these two methods to develop our typo inference. And Haskell is an example for constraint-based method. And the most important thing is that we want our inference algorithm to support gradual typing. Now let me give a brief introduction for our algorithm first. First, the bidirectional typing do type inference by propagating typing information and report static error if the propagation fails. And constraint-based methods use type constraints to solve types for unknown position in an expression. And if constraint solver fails, it will also report a static error. So both of them do not support gradual typing. In our typo inference, we integrate these two methods together. In general, we use typos to represent unknown types, then follow bidirectional typing approach to do basic type inference and type checking, but add a layer on top to use the constraint-based methods to solve types for typos. And if the constraint solver cannot find a proper solution for all typos, we will delay type checking to runtime rather than report a static error. So in this way, we can support gradual typing. And now let's walk through some examples to illustrate the algorithm in detail. First, we will attach type variables to each typo, like variable A and B in this figure. Typo is inserted automatically by system, so programmers can omit most of type annotations. Then we propagate typing information, which is similar to bidirectional typing approach. Here are two general forms for bidirectional typing rules. We extend them with type constraint set, which is capital C here. It represents a set of equations to show type consistency between type variables and basic types. Here is an overview of our modified version for bidirectional typing rules. And we will use those rules to do type checking and generate type constraints at the same time. Those type constraints will be used to solve types for unfilled typos in the step 3. We can take expression 2 as an example. This is a propagation process for expression 2. We can say that the propagation can get some type information for this expression, and also it outputs a type constraint set, and this type constraint set can be used to solve types for typo A. In general, the step 2 may fail at propagation, like expression 1, because the expression 1 cannot match the plus bidirectional typing rules. The true cannot be analyzed against non-type. So in this case, we will report a static error directly. In the other two examples, expression 2 is just a plus expression, and expression 3 is in fact an invalid expression because x serves as function and a non-type at the same time, but both of them will succeed in propagation. if we write rows out. And it will get some basic type information and a constraint set. Then we pass this constraint set to step 3. Use unification algorithm to solve this constraint set. And the constraint set may be solvable, like expression 2. Then the front end of the Haskell will show a suggestion for this typo, like green here. And we can press some shortcut key to turn this suggestion to concrete type in our program. And the constraint set may also be unsolvable. Like here, the typo B cannot be int and arrow type at the same time. So we will keep this invalid part as typo and postpone type checking to runtime. The GHC Haskell support similar techniques for typos. We can use an example to illustrate difference here. Here, f and g are two functions. Use int and bool relative as input argument. And function h use the undetermined type as an input argument. And in the function definition for h, the application fm will generate constraint that typo a is consistent with int, and function application gm will generate constraint that typo a is consistency with bool type. There is conflict here, so the constraint solver cannot find a proper solution, and the GHC will fail at compilation. However, if we give a proper value for h and z here, the program should run successfully in runtime. This is what we want in typo inference. On the other word, that is to support gradual typing. And this program will succeed in propagation, so the compilation succeeds. It only fails when we try to solve type constraints for the typos, but we just delay type checking to runtime in this step. And Zach already do some work on gradual typing inference. His approach is very similar to the constraint-based type inference, but he used the idea of the less equally informative type system and built an advanced constraint generator and solver to avoid programs like this to be rejected during compilation time. But since it uses constraint generation and solving to do type checking, so it's hard to do error locality. But it can reject more bad programmers at compilation time. For example, the expression 3 in the previous slide will be rejected during compilation time in Zach's approach. Our approach simply drops this case into runtime tracking. So this is kind of limitation in our approach. In the future work, we will implement this feature into Haskell project. And there are also another problem, that is the constraint for typos may be under constraint. That is, there may be we cannot find a solution for typos, like this identity function. We may solve this by introducing polymorphism into Haskell project. Thank you.
Thank you. So, we have question from Yao Li. So do you want to unmute yourself and ask your question? Yeah.
Oh yeah, sure. Yeah, I'm just it's not very clear to me, but it's probably I'm not I don't know much about Haskell. So, what kind of type system does this inference algorithm support? Like, for example, does it have subtyping? Does it have polymorphism?
No, it does not support this tool now.
Okay.
This is a project that introduced typos. Typos is you can use host to represent like unknown types or unknown expression.
Okay.
And it not only use bidirectional typing for type inference. So we cannot solve types for typos now. And what we want to do is just use typo inference to solve types for typos.
I see. Thank you.
Any other questions?
Yeah, maybe. So you're mentioning here polymorphism as a possible solution to a problem you're having currently. But I was wondering if it would also introduce new problems, because then you get, once you have polymorphism, you get more possible solutions. Like if there's already type variables in scope, then these could also be valid solutions.
Yeah.
And then you have to choose between more options. So have you thought about that problem?
Yeah, but we want to use a user front end to like show a list of possible types for a typo, so user can select from those.
Right, but that might become a very long list if it's,
Yeah, that's right. This may be something we will think about in the future.
I also have a question.
Okay.
So the algorithm for deferring to runtime seems a little bit. Well, I guess do you have a sense of how often the type checking has to defer to runtime? Like how much code have you written in this language?
We didn't do such tests before, but compared to Zach's approach, our approach certainly will postpone more expression to dynamic type checks.
Okay, but you have a sense of how much will get deferred to runtime? Because I think that would be interesting in terms of you know, the practicality of the language and of your algorithm.
I think it's determined by how well the program is annotated. Like if there are more holes in an expression, there is a large possibility that the expression may be deferred into runtime checking. Yeah, but how many percentage, I think it's hard to say now.
Okay, thank you.
Okay. So I was wondering, what is the target of the Haskell programming environment? Is it for beginning students?
Yeah, this is one of the purpose it will use in our programming course in UM, and it also is a structure editor. So each status of the in Haskell is a valid status because you can turn the invalid part as a whole in the Haskell program. So
yeah.
So in this case, you can keep some part of the expression under development and keep working on other parts.
Okay. And my question is, so putting type holes means you first think about the code and then its type, right? In some sense.
Yeah. I'm not sure I understand what you mean.
So some people say you should first determine the type of your function and then write the code. Right?
Yeah.
But in Haskell, we can defer the decision of types at some later point, right?
Yeah.
And I was wondering if this is easier for beginner or not.
Oh, that's a good question.
Yeah, maybe you can do some kind of experiment.
But I think our typo inference well, give some suggestion for the typos, like showing this figure. This is a gray part. It's just a suggestion for the typo. We did not turn this incomplete part to a concrete part. So maybe it will give the beginner some idea what should be filled in this part.
Yeah, sounds good. Okay, thank you, Zhiyi.
Thank you.